I'll start by saying it's not going to be a research talk at all. Though the motivation comes from some research problems I'm working on at the moment. So the point is basically I need to understand this notion called translation functors, which is an important notion in Lie algebras in the context of certain tensor categories called Kasdan-Lustig tensor categories, or certain categories equipped with a tensor product defined by Kasdan-Lustig. Now, I'm not going to talk about that today. I'm instead going to talk about the classical story, translation functors for categories of G modules, where G here is a finite dimensional simple Lie algebra. So the comparison between these two is that in some sense this is an affine context. So this notion of finite dimensional simple Lie algebras and also affine Lie algebras or affine Kac-Moody algebras. Now, there is a theory of translation functors for affine Lie algebras, but it's really not this that is the point here. So the thing with affine Lie algebras is that a certain parameter called the level enters the story. And when you take the tensor product of two modules of the same level, you get another module but of twice the level. So if you fix the level and you want to study the category of representations of a given level, the usual tensor product isn't really very good. So Kasdan-Lustig defines some more complicated tensor product, which involves looking at the Riemann sphere with various punctures, look at spaces of functions on the sphere, and use this somehow to cook up this tensor product between modules at a fixed level. Well, anyway, that's enough about the motivation. So I want to describe the classical story today. So G is a finite dimensional simple Lie algebra. And so as usual, there's a triangular decomposition, which I'll write like this. So for example, G is SL2. Then this is spanned by, I'll call F, H, and E. And in this case, triangular decomposition is like this. This is N minus, this is H, this is N plus, upper triangular, diagonal, and lower triangular matrices. So I have this notion called Verma modules. So the idea here is to fix a weight. A weight is an element in the dual of the Cartan subalgebra. Grab a vector and let call it V0 and let H act by this character, or this given by this weight, and declare that N plus is going to annihilate the vector. And then induce obtain a G module, which we call M of lambda. This is the Verma module. So the idea of inducing is that it's kind of, in a sense, well, formally, it's defined by this. It's, in a sense, free over n minus. So in the case of SL2, this kind of looks as follows. So we could define, take lambda to be a function which sends h to 3, for example, v0. And then if we try to apply e to v0, we'll get nothing by definition. But if, on the other hand, we apply f, we're going to get a string of vectors to go on forever in principle. And E is now going to come back like this. So what are these vectors? So what I'm saying here is that H acts on this vector by 3. Now when you apply F, that changes the eigenvalue. So now H is equal to 1 on this vector, minus 1, minus 3, minus 5, minus 7, etc. So these arrows are essentially by definition, and then these arrows going back up are going to have coefficients determined by the commutation relations in the algebra. And it happens, in this particular case, that when you pass from here to here, the coefficient that appears is going to be 0. So what you have actually is a submodule. So this part of the vector space spanned by all of these vectors, you can get into it starting from the top vector, but you can't get back out because this coefficient is 0. So let me call this vector here sigma. So we call this submodule n. So it turns out that n is itself isomorphic to a Verma module. This time it has highest weight minus 5, and it goes down from there. Well, the other thing that happens is that n is irreducible, unlike m itself. So what we have is a situation where we have a submodule or a string of submodules like this, and all of the quotients, I call this m, okay, so such thing is called a composition series in algebra. everyone knows what a composition series is. It's a sequence of subspaces like this, such that consecutive quotients are irreducible modules. And the basic question is, so we have this class of modules called Verma modules. Can you say what the composition series of a general Verma module is? So a little bit more precisely, we can first, well, let me give you a fact. So each Verma module has maximal proper submodule n. Well, I suppose it also depends on lambda, so I'll call it n lambda. And then obviously, the quotient is irreducible. So the irreducible modules that occur as composition factors of Vermas are all of this form for some other weights. So the question really then is, you fix lambda, you look at m lambda, and you ask which L mu's can occur in it with what multiplicities. This is something that just depends on these two weights, lambda and mu. Now, first observation along these lines is that if a given L mu appears as a composition factor, then simply by composing with the projection from m mu to L mu, you'll get a map from m of mu into m of lambda. Okay, so that's really our question. For which pairs lambda and mu do there exist morphisms from m mu to m lambda? And now, this preliminary question is quite easy to answer. So let me do this also in an example. So look at SL3 now instead of SL2. Okay, so now our H joule is two-dimensional. So inside this space, I'll draw H joule here. So inside it, we have firstly two roots, alpha 1, alpha 2. Simple roots. let's consider the dual basis, which is, called the fundamental weights, which is this basis dual to the roots. So let's see, so these are here and here. Now I'm going to define P plus to be the positive integer span of these fundamental weights.
Can you describe the map in the second line? So there's a map from mu to L mu by definition. And what is the map from L mu to m lambda?
This is if it appears as a composition factor.
Which you defined this Li being, for example, one of these quotients, mi divided by mi plus 1, I guess.
Mm-hmm.
Then from mi, there's a map to m. Therefore, from mi divided by mi plus 1, there's a map to m divided to mi plus 1.
Right.
And how are you inferring that from there, there's a map to m instead of to m? Or are you lifting the mi plus 1?
Yeah, I think it's not entirely trivial. But yeah.
Yeah, so perhaps saying that these quotients are always split, that the sequences are split. So this, I mean, the fact that in this row you have this vector space of dimension 4 inside of this infinite dimensional space,
Mm-hmm.
that you can view it as a quotient or as a submodule itself.
This here.
Right, so that quotient is L,
Yeah.
which is of dimension 4, but you can also view it as a subspace of the infinite dimensional space.
Wait a second, is it?
But that's not true because,
Yeah, it's not true.
so,
Yeah, I mean, right. I don't. I don't think it's obvious that there's a map from the Verma module. I mean, there are resolutions by Verma modules, but that's in a sense an independent statement. Yeah. Yeah. I mean, there's a lot of facts here that I'm not really going to prove. I'm just stating. All right. So. Firstly, right, so I'm going to restrict attention to so-called integral weights for a start. So these are weights that are in the Z span of these fundamental weights. So this is important partly because so if you ask the question, what are all the irreducible finite dimensional representations of G, it turns out that they're all the L lambda, where lambda ranges over this set. So that's why this set is important. I mean, somehow, too, for what I want to say, it doesn't matter whether there's a morphism from the Verma or not. A morphism from the irreducible suffices. Anyway, suppose I took a weight, like this weight, for example. I want to consider, so I'll call that lambda. And so I want to consider L of lambda, which is quotient of M of lambda. So M of lambda is given by saying that all raising operators, so root vectors with positive roots, are going to annihilate this weight. And then we generate freely by the negative root vectors. And the question is, well, the first question is then, in what possible weights can a M lambda map into M mu map into M lambda? Okay, so the first fact is that such mu actually have to satisfy a condition, which is, if we define this vector rho to be, so it's called the Vowel vector. Then the inner product between mu and mu plus 2 rho has to equal the same expression for lambda. So this is a quadratic relation on mu. It turns out it's positive definite, and so it defines kind of a ellipsoid or sphere in this space. So in particular, you can deduce that only a finite number of integral weights mu can satisfy this condition. In fact, it's going to be a sphere centered on minus rho. So the second fact is, well, we have to introduce a so-called Vowel group at this point. Which is the group generated by reflections in the simple roots. In this case, we have two simple roots, alpha 1 and alpha 2. And so the Vowel group is generated by reflection in this line and reflection in this line. So some finite subgroup. Okay, so all throughout Lie theory, this so-called shifted action of the Vowel group appears and is very important. So we give it a name and call it the dot action. So it's somehow not so surprising that, well, the relation between these two is the following, right? So these reflections preserve the inner product here, and so it's pretty clear that these shifted reflections are going to preserve that quantity, taking lambda times lambda plus 2 rho. And so in this case here, for example, this reflection, I actually want to draw this diagram correctly here, so. In this particular case, the weight lambda that I took, so I took it to be one of the fundamental weights here. But these reflections are going to be centered around minus rho, which is down here. So lambda is kind of around here. And then its images under this group are going to be down here. Then reflect in this plane. Or we could reflect in this plane directly. We'll come over here. And that circle is the set of vectors that satisfy the quadratic equation. Okay, so roughly speaking, how are these facts proved? So starting from G, we form this associative algebra called the universal enveloping algebra. Inside there, if we take a basis of G and a dual basis relative to this, relative to the killing form, let's say, can form this element. It's called the Casimir operator. And it turns out that it's actually in the center. Hence, since it commutes with the action of all elements of G, it acts as a constant on any Verma module. But let's think about how it acts on the top, on the generator of the Verma module. So we can take a basis of H, take a basis of root vectors of n plus, and then the corresponding dual vectors of the root vectors of n minus. So if you take omega, which now looks kind of like this, and apply it to this highest weight vector, then this part's going to go to 0 because the positive root's going to annihilate the vector. This part's, is not going to go to 0. This is, well, it's going to be something like, actually it's going to be exactly lambda with lambda. And for this part, you have to swap the order of the two terms. So this looks like E minus E plus some term H alpha lying in the Cartan subalgebra. This part will again go to 0. And then the sum of these guys, also acting on this highest weight vector with weight lambda, is where this term rho comes from. Okay, so the Casimir acts by that constant, lambda plus 2 rho on V naught. Therefore, it acts by the same constant on all other vectors in the Verma module. But now, if you have inside this Verma module some other weight mu, then exactly the same argument says that the operator has to act by mu times mu plus 2 rho on that vector, and that's how we get this equality. So the second part is proved by a refinement of this idea, though there's several other new ideas involved as well. Essentially turns out to be isomorphic to W invariant polynomials on the Cartan subalgebra. Now there's somehow this isomorphism also includes, it's not so obvious, but it also incorporates this shift in some sense. So, well, In the same way as before, the Verma module determines a so-called central character. Chi lambda, which is now mapped from the center to C, homomorphism, which is determined exactly as before, taking an element to the center, letting it act on the Verma module. It acts by some constant. And then the consequence of Harshchandra's isomorphism is that chi lambda and chi mu are equal if and only if Okay, so also some terminology. We say that weights are linked if they bear this relation to each other. Okay, so before going further, I should introduce another piece of terminology, which is to say exactly what sort of category of modules we're talking about. Because I'm talking about Verma modules, so I certainly want to consider Verma modules. I'm also talking about irreducibles. And I've said the only irreducibles that are going to occur are those that are quotients of Vermas. And it's certainly true that there are many, many, many more irreducible modules than those. And in fact, it's kind of one of these funny, well-known facts that for SL2, all irreducible G modules are classified, but already for SL3, there isn't a classification of all irreducible modules. So it's good to establish, in a sense, the category of modules that we're going to work in. And the right category is the so-called category O. So this is the category of G modules that have, they're weight modules. So they have a decomposition into weight spaces. They should be finitely generated. As a G module. And the action of the positive part of the algebra should be locally finite. So this is saying that for all m in my module, if I take m plus and apply it to m, this defines some vector subspace, and I want to say that its dimension is finite. So this says, in a sense, that modules kind of look like this. If you try to go up too far, you'll eventually get to 0, and there's some finite set of vectors that generate the whole thing. So then the kind of the statement that comes out of what I've said so far is that category O splits into a direct sum of subcategories that are called blocks. The subcategories And basically, these categories don't talk to each other in some sense. So that is to say, there are no non-trivial morphisms between modules in one category and another, in different blocks, that is. So it kind of suffices to understand these blocks. Okay. So now I said that the first thing I wanted to say was to kind of mention this Kasdan-Lustig theory. So let me mention it. So it turns out okay, so where are we so far? So the problem is for a given block O lambda, describe which composition factors, and the composition factors are going to be of this form, that occur in M, so which order should I do it? Okay, so we've got two finite sets here, parameterized, well, two copies of W in a sense, and we want to understand the relationship between them. So one is the set of Verma modules associated to elements of the Vowel group in this sense, and the other is the reducible modules. Okay, and the answer, which is conjectured by Kasdan and Lustig and then proved very soon after by Kashiwara, Brzezinski, and Bailenson and Bernstein, is essentially combinatorial in nature. So it involves the combinatorics of the Vowel group. So let me sort of just say what the answer is. So in this case, so we had these weights. Which are obtained by starting with lambda and then applying reflections. Like this. So for example, we get to this bottom weight by applying triples of reflections in two different ways. Here, simple reflections. And so what this gives is, so how do I want to say this? So there's a length function on the group, which is given by counting how many simple reflections it takes to get your element, right? So here, well, 0, because it was just the identity. Then I could apply one reflection, or one reflection here, two reflections. Finally here, I got 3 reflections. And this corresponds to an order on the group. So we have the identity corresponds to 0, 1, 2, 3. The two simple reflections have length 1, obviously. Of length 2, there's these two products. And of length 3, there's the single element, which can be written in two different ways as product of triples. So this element the so-called longest element of W, we call it W0. So this cache-journalistic formula, which is now a theorem, says the following. Okay, so the most convenient way to phrase it actually is to, rather than starting at the top, to start at the bottom. So let me call lambda 0, W0 applied to lambda. So that's this weight here. So two of these regions here, these segments are called chambers. This is the positive chamber. This is the negative chamber. So we go down to the negative chamber, call that weight lambda 0. So that module, the irreducible module, is very simple. It's just equal to the Verma. Or to say it another way, the Verma is already irreducible. And then the formula kind of says what happens as you go back up. So if you look at L, apply W to L lambda, then it's going to be equal, in a certain sense, to a sum. The sum runs over y, which are less than W, in this kind of partial ordering, which induces this length function. It's going to be a factor, length of W minus length of Y. So a formula that kind of expresses irreducibles in terms of Vermas. Now, what do I mean here? Obviously, it's not an equality. It wouldn't make any sense. But what I really mean to say is that you can associate to each module a sort of graded dimension called the character. There's going to be an equality of characters. Of characters. So what is a character? So let me give an example. So M3 kind of looked like this. What we do is invent a formal variable that parameterizes these points. So we say x, so we'll call this x cubed, x1, x minus 1. So then the character is x cubed plus x minus 1. So we could rewrite this as a rational function like that. So the formal character. So we saw that the irreducible quotient, L3 of M3, had character x3 plus x plus x minus 1 plus x minus 3.
Is it divided by 1 minus x minus 2?
Oh, thanks. Yeah. This is now, well, chi M3 minus chi M minus 5, right? So, or to put it another way, at the level of Grothendieck groups, we have this equality that L3 equals M3 minus M minus 5. And you get that out of this sum here. See, the irreducible is given by a difference. In this case, the Vowel group just consists of two elements, the identity and the reflection. And the dot action of this reflection gives us the 3 and the -5. And there's a sign appearing. But what is this p thing here? So in this case, it's just 1. But in general, there's some complicated polynomial. These are the famous Kasdan-Lustig polynomials. So in general, these are polynomials with integer coefficients, and for either, I'm not sure if they're good reasons or historical reasons, but it's usually written as polynomials in q to the plus and minus 1/2. And kind of the explicit definition of these polynomials is pretty complicated, and it involves a kind of algebra called the Hecke algebra. So the Hecke algebra can be sort of obtained by looking at double cosets of corresponding algebraic group to G and looking at it over finite fields and kind of writing down formulas for the product of double cosets, doing this over different prime numbers, then replacing the prime number by a formal parameter, which becomes Q eventually. You end up with this kind of, in a sense, Q-deformed group algebra. Then it has kind of a natural basis, and it has some other more subtle basis, which is invariant under a certain involution introduced by these guys. And it turns out you can write down this change of basis matrix between the two in this recursive fashion. The coefficients then are these polynomials. They turn out to be very difficult to compute in general, like quite computationally expensive to compute, but they can be computed explicitly. So then you put q equal to 1, and that's the number that appears here. So a special case of this formula is given by going all the way back up to the top weight, well, the original lambda that I just erased. Then in that case, W is the longest element in the Vowel group. Oops. Which is the original finite dimensional module. Which is a classical and very important result called the Vowel character formula. Well, okay, so as I said, the statement of this formula is this completely algebraic / combinatorial fact, but the proof turned out to involve very difficult geometric methods, and this was kind of the point where D-modules entered representation theory of Lie algebras in a serious way, and this spawned this entire so-called geometric representation theory revolution, which I'm not going to talk about. But as I said in the abstract, what I wanted to do really was to talk about somehow a shadow of this, so-called translation functors. So aside from have an explicit formula here relating vermas and irreducibles, somehow the lesson that you can draw from this formula is that the structure of this block, O lambda, kind of doesn't really depend on lambda. So kind of you had lambda here in the formulas, but all the coefficients, sort of all the sort of expansion of one module in terms of another, depends on where those modules are in relation to each other in this combinatorial ordering on the Vowel group. So everything reduces to this kind of structure depending on the Vowel group. So that means in particular, one expects these blocks to be kind of the same, or indeed even isomorphic or equivalent as categories. And what translation functors give you, so this was kind of the state of the art in this theory just before this entire Kazdan-Lustig story broke. Translation functors basically are equivalences of categories between certain blocks. I mean, they're actually a little more general than this, but I think that's the kind of the best way to think about these. So okay, so this is the moral, is that these blocks have a structure which is basically expressible purely in terms of the Vowel group, and so shouldn't really depend on lambda. And yeah, there are some caveats that when you go to these so-called walls, which are these points where the Vowel group action is not regular, what I'm saying gets more complicated. I mean, it's still included in this Kazdan-Lustig story, but what I'm going to say next is not quite true. Let's say dominant. Actually, let's say lambda and mu are integral as well. This is also not essential, but just to simplify things. So we'll take lambda and mu both in this kind of set P plus. So they're integral. They're in the same cell of this diagram. Then, in fact, these categories are equivalent. Furthermore, there actually exist adjoint inverse equivalences, and these are the so-called translation functors. We call them T, lambda going to mu, and T, mu going to lambda. Okay, and how are they defined? So take some module in this block, O lambda. Oh, yeah, okay. consider the difference between these weights, mu and lambda, call it nu. Then if you take the Vowel group acting on nu, so this is the usual action, this is not the dot action, then there's some finite set. It turns out the elements are also integral weights. And it turns out that the intersection with P plus is unique. So this is going to consist of a single element, which I'll call nu bar. Then since it's in P plus, the corresponding irreducible module is finite dimensional. So now we take our module, we take the tensor product with this irreducible module. So now there's another G module. It'll consist of a direct sum of various components which are all in different blocks. So you take the projection to the block O mu. Well, this, by definition, will be T lambda mu. So it's basically tensoring with an appropriately chosen irreducible module. Okay, so why would you do this? Well, as I say, these are going to turn out to be equivalences between these categories. So in particular, they're going to take Verma modules to Verma modules. So that's the first proposition. Sorry. Actually, I totally forgot to ask. Is it 1 hour or an hour and a half?
Until 5.
Till 5? Okay. Okay, so I think what I'd like to do is try and explain the proof of, not this theorem, well, of a special case of this, which is that in particular, if we just take the Verma m lambda and apply the translation functor, we get m mu. But the same is true if you go to other W images as well. So it depends on a couple of lemmas, one of which I want to prove, if there's time. Okay, so here we're saying, so we have this finite dimensional module, L nu bar. So it consists of some finite collection of weight spaces. And if we look at the weights, such those weight spaces are non-trivial, nu prime is one of those, then we consider whether lambda plus nu prime is linked to lambda plus nu. This turns out to be the case if and only if nu prime is nu itself. So the first fact is the really key technical lemma. The second is well, kind of a not key technical lemma. Second one is very easy. It's just given by inducing from the modulo over n plus. What it's saying is that, what I meant to say here is of L. So in particular for L of nu bar, but for any finite dimensional module, in fact, when you tensor a Verma with such a thing, so L itself has a collection of weights with multiplicity. M will have some filtration such that the quotients are themselves Verma modules, and the highest weights of those Verma modules will just be lambda plus the weights of L with multiplicity. So it's what you would expect, and it's very standard. Lemma 3 is a classical fact in representation theory, is that the weights of this lie in the convex hull of the W image of nu bar. And the kind of extreme points in this convex hull, which are the images of nu bar itself, have multiplicity 1. So, for example, just to kind of make this concrete, so if I take nu bar here, you'll kind of go down in steps of roots to the reflection of this weight here. And there's another reflection there. So you have some kind of setup like that, convex hull. So you get weights in the interior as well. Oh, how does this go? Did I miss one here? Sorry, the diagram's a bit crooked. And the multiplicity, so that's the set of weights that occur in this module. The multiplicities are 1 along the edges, it turns out. And then increase as you go down inside the shells in this module. So here the multiplicity is likely to be 2, it turns out. All right, so in particular these weights in the W image, multiplicity 1. And so with those 3 facts, we can easily prove the proposition. Okay, so this is the definition. So now we're taking a Verma, tensoring it with a finite dimensional module. So this here has a filtration with quotients Vermas lambda plus weights of L lambda bar, nu bar, right? Now the first lemma says precisely that out of all of these nu I that occur, the only one which is linked, or the only one which lies in category O mu, is the one that corresponds to mu itself. Whoops. So this means, all right, so we have that. The next point is that by the third lemma, that particular Verma module only occurs once, right? So if it could occur multiple times, in principle, you could have an extension of that Verma by itself. But you actually don't. You only have it occurring one time. So we get m mu plus stuff outside O mu. And this stuff is in different blocks. So the projection mu as required, okay? And so by kind of more complicated argument, as I say, there's a similar lemma for other W images of lambda and mu, which implies the more general version of the proposition. The next point is that the translation function also takes irreducibles to reducibles. And this one is more general as well. So this one I have to be a bit more sketchy because I haven't introduced part of the necessary theory. But first fact is, well, these functors are exact. So if we look at the quotient map from m lambda to L lambda and apply this functor to it, then we're going to get a quotient map from m mu to the image of this translation functor. So you also have to think about duals. So just as the Verma module has a unique simple quotient, it's believable that the dual of a Verma module has a unique simple submodule. Which it turns out is isomorphic to the corresponding irreducible quotient. And furthermore, any non-trivial morphism from M mu to its dual actually turns out to have image given by this irreducible submodule. I'm sorry, lambda. Okay, so now we use exactness again. So we have L lambda mapping into the dual of M lambda. Then we apply the translation functor. We get an inclusion into the dual of the image of M lambda, which is M mu. And composing them, so it's easy to see there are only two options, that the image of L lambda has to be either L mu or 0. So in principle, either of these two things could happen. And to show that it's the former and not the latter, we just have to, well, obviously we have to exclude the case of 0. So how does that happen? Well,
doesn't that follow from that? And you know that it sends vermas to vermas.
Sends vermas to vermas.
And if it sends, so if you take the morphism from the verma to the irreducible, and look at the short exact sequence for that, and if the irreducible goes to 0, then I think you can't preserve that sequence.
Well, it's a priori you don't know what happens to the kernel. I mean, in principle, it could become isomorphic to the image of the. It could become a verma, right?
It could become the verma.
Of course, it doesn't, but a priori it's not clear. Yeah, I mean, there's something to prove. But yeah, I mean, it seems absurd that it would happen, and indeed it doesn't happen. So why precisely? Well, if you look at characters, you can see it easily. So in fact, here I'm going to use the fact that these are regular weights. So then, in this case, the characters of the vermas span, actually I shouldn't, it's kind of awkward. I don't want to say characters, I want to say the classes generate over Z, the Grothendieck group. So in particular, these induced maps, induced from lambda mu, mu lambda, are inverse isomorphisms of abelian groups. So basically, look at it at the level of Grothendieck groups. And since irreducible module is not 0 there, its image can't possibly be 0 as a module. Therefore, it actually has to be L mu. So that completes the proof. So, well, yeah, perfect time to finish. I was actually going to, I'd sort of wanted to explain the proof of that key lemma, which I guess, what was that? Was it lemma 2, I think? No, lemma 1, about linkage of weights. So there's absolutely no time, and the proof is quite complicated. It's sort of combinatorial argument involving Vowel groups. And it's kind of, the rest is all formal nonsense. So I've described the formal nonsense. I haven't described the key lemma, which really makes everything work. But, well, for anyone who's interested, I can give a reference, of course, and can explain it any time. But anyway, I'll finish there. Thanks. No.
I was thinking about your last statement there, that this, the duo of mu has subordinates mu.
Yeah.
Doesn't it
Actually,
duo of mu as well?
Yeah. Yeah, it's a good point. So this dual is not the dual in the usual sense. So if you take the dual vector space of a Lie algebra module, that of course is a module of the same Lie algebra in a canonical way. This dual is a kind of twisted version of that, which is designed to preserve category O. So in the usual sense, what you're describing is if you look at L lambda, just take the dual vector space, this turns out to be isomorphic to L minus longest element of W applied to lambda, which you can see by, well, the set of weights of this are simply the negatives of the set of weights of L lambda. Yeah, and then, well, it is what it is. So this dual is defined by composing that dual with an involution in the Lie algebra that exchanges the positive and negative roots. And you kind of have to do this to work in category O, because if you have some module that looks like that, and then you take the dual, then it's going to have weights that go upwards, and it's no longer in category O. So this is why they do this. They flip the positive and negative roots to bring it back down. And then with that duality, it is actually true that these irreducibles are self-dual. Yeah. Yeah, it's a good point.
Any more questions? You started by saying something about Cauchy-Lustick's tensor categories.
Yes.
So the category of just G modules, or it's stable under tensor products. Not each block, but G modules have tensor products. How do these functors play with that tensor product?
With the Cauchy-Lustig?
Which is the usual finite dimensional G modules over a finite dimensional Lie algebra, and you have these T mu lambdas that you defined.
Mm-hmm.
Do they play nicely with the usual tensor product of modules in category O?
In this story, a finite dimensional Lie, do tensor products play nicely with? I don't know. I never thought about it. Like, if you, I don't really know. The idea is you start with one block, tensor with a finite dimensional module, you get a sum of things in all sorts of different blocks, and you're interested in a particular other block, so then you just project to that one. More, I don't know. What else can you do?
Well, if you have two Vermas, say for lambda and for mu, if you take the tensor product, you know you're going to have one particular weight, a higher one, and you can apply lambda to gamma, mu to gamma, or take the tensor product first and then apply these T functors, or you take first the T functors and then take the tensor product.
Ah, okay.
And at least certain projections, you have a conjecture that prove that.
Well, if you tensor, so it's take two guys in the same block, tensor them. So you've already got something which is
in different blocks.
Okay, two guys in different blocks. The result is now spread over all kinds of blocks.
But you take one of them.
Take one of them. So you've got, what, like lambda 1 and tensor something in lambda 2, and consider some other block, mu, yeah?
Something like lambda 1 plus lambda 2 or something like this. And
Okay, yeah.
And you can just apply a t functor to that.
Mm-hmm.
Or you could have taken the t functor.
Whoa. So you take the tensor product, it's here, and now you apply
t. Some t.
t mu,
Whatever, yeah.
some other, yeah, okay.
Or you could have just taken different t's on these two guys and then take the tensor product of those.
Yeah. No, well, yeah, I don't know. I think it becomes kind of chaotic because everything ends up in lots of different blocks. But yeah, truth is, yeah, I don't know. I haven't thought about it. Yeah. So I could comment. So you mentioned Kazdan-Lustig, so I could comment that there is such thing as affine translation functors, which really is you just look at modules for the affine Lie algebra at all different levels. And yeah, if you have two dominant integral weights, then their difference again has some element, some Vowel group image, which is a dominant integral, and the corresponding module is integrable. It won't be finite dimensional, but it will be integrable, which is kind of just as good in some ways in the affine setting. And you can still tensor with it, and most of the theory goes through. But the really difficult part is if you want to do something that works at a fixed level, then you have to go into this geometric Kazdan-Lustig story. And since the tensor product itself is defined in this very abstract way, kind of as a representable functor, it becomes quite difficult to see really how to push through this theory. But it's been done. I should say, I mean, the reference is Frenkel and Malikov. This is paper of Frenkel and Malikov, which basically I'm trying to understand at the moment. So, yeah.
So you mentioned as well that you produce something that the number is not regular, it's on the wall, right?
Yeah.
Can you say if you
So I'm not so familiar with that part of the story, but I think the history is that kind of, so before this Kazdan-Lustig story came about, Janssen had made a lot of progress towards it. And like in some sense, Janssen's methods are basically translation functors. I think it was Janssen that introduced these. And the idea was to kind of start in the regular block, and you have these equivalences of categories between different blocks. And then the key thing to understanding general blocks was to kind of translate from something here to the wall. And actually, I forget if it's better to translate down or translate up. I think maybe it's better to translate up to a wall. But the point is, most of the theorems that I described here, which I only described for regular weights, also carry through in a slightly more complicated form for these kinds of translations, going from a chamber to a slightly more singular chamber, or to a wall, that is. And similarly, when you go from a sort of a volume to a plane to a line inside it. I don't really have anything specific to say, but in a sense, the theory was designed to do that kind of thing, to literally to translate the nice properties from the regular chambers to the singular ones.
But then it's not an equivalence, right?
It's not an equivalence anymore. Yeah.
And you cannot get out of the wall, right?
Right. Translating into walls is good.
But you have one adjunction, right? So you can always induce up.
Well, yeah. But somehow, like when you're on the walls, it's harder. So the idea is to extrapolate from what's well understood in the regular part and use that to deduce something about the wall. But yeah, it's true. I mean, you get adjoint pairs.